who you all know, Naomi Aoze, who came to us from a postdoc at Caltech. And since she's been here, she's won awards and all kind of stuff. And so, and don't snowboard, okay? So don't snowboard. But see if she can get through this talk without breaking anything.
I'll try my best. So I was supposed to travel around and give some talks, but like my doctor said, I cannot travel for a while. So I am here giving the talk to you instead. Okay, so it's always fun to be at the control seminar. So thanks for Jim and Vasilios for organizing this. Today I will talk about some fundamental limitations of learning for dynamics and control. So learning has been, there has been many advances in machine learning in recent years, and it's also influencing what we do in control in many interesting ways. As a community, we are taking advantage of these advances, but there are also some limitations, fundamental limitations that arising from dynamical systems. One thing I have been thinking about in my group is to understand these fundamental limitations so that we can be more informed in using this learning methods. So this is a quick outline of the talk. I will start giving some examples of learning in dynamics and control. Then on the technical part of the talk, I will talk about mainly two results. One on some fundamental limitations of learning immersions. This has some implications on learning Koopman embeddings. Then I will talk about hardness of learning to stabilize for simple linear systems. Okay, so this is our typical control loop. We have a plant operating in some environment. There could be disturbances coming from the environment. We have some task or mission specification. And we are trying to design this controller so that when we close the loop around this plant with this controller, it satisfies the mission specification. And many of the components in this control loop can be learned. So we can learn the plant model. This is your classical system identification. We can learn the task specification. This is inverse optimal control or inverse reinforcement learning. We can directly try to learn controller from data. Maybe this is your model-free learning or direct data-driven control. And one thing that's not shown in the figure is typically our controller does not directly measure the states, and you have some perception estimation module in between your plant and controller, and you might be learning that as well. And overall, our goal is to ensure system-level safety and performance when some of these pieces are learned. So we know how to do these things when we have models of all pieces, but we want to be able to do it when some of the pieces are learned as well. We try to do that in many different settings, and I will show some examples mostly from my own work with my group. So here's an example where we are trying to steer a rope. It's, if you will, an infinite dimensional system, very complex dynamics, so it's hard to write down the dynamics of the rope. And here we are trying to learn the dynamical model of the rope using a neural network. And we are quantifying some error around this learned model. And with that quantified error, we can design new algorithms for doing planning, and we can take this rope and take it to a target position, avoiding obstacles that are shown in red here, and achieve the task that we want to achieve. Here's another example where, again, we are trying to do some path planning in an obstacle environment, but our only way of localizing is these low resolution images. So the robot takes these low resolution images, and we are learning a perception module that takes low resolution images and gives us a 2D position. And we have 3D versions of that as well. Then we quantify the error that perception module has. And with that error quantification, we can design planning algorithms again, that achieve correct planning, obstacle avoidance, and goal reachability with some guarantees. Here's another example where we are trying to learn a task specification. We have demonstrations in a VR environment. A person comes in, they pick up a soup can, they place it in some small box, they deliver it into a blue region, then they pick up a Cheez-It and do this multi-stage task. We represent this multi-stage task in the language of linear temporal logic. We learn this logic specification from the demonstration. Then we can deploy it on a real robot in the real world, where maybe the robot changes itself, maybe the environment changes, but task is the invariant here. And once we have the task description, we can deploy it in a new environment. In all of these examples, what happens is that there is a data collection process, there is some learning process, and sometimes that learned thing works. If it works, we try to do our uncertainty quantification on the learned thing. If we can do the uncertainty quantification, we can go ahead and verify and close the loop. Then we have a result, we write a paper, we are happy. This is the good scenario, but typically there's a bad scenario there as well. Oftentimes we try to learn something and it doesn't converge. Or we try to learn something, we think we learned something, we try to verify or quantify the uncertainty, and the uncertainty is too large. And in these cases, we typically don't know whether we did something wrong with learning. Or whether there's a fundamental limit in terms of what we are trying to learn. And I think this is very typical frustration of people trying to do learning for control tasks. When it works, it's great. When it doesn't work, you don't know if you need to tune your hyperparameters for 2 more weeks or whether there is something wrong fundamentally. And we are trying to understand whether there are some fundamental limits so that we can provide some guidance to people who are trying to use these learning algorithms and say, okay, for these classes of systems, maybe don't use this class of learning algorithms because they won't provably work. And I will describe what not work means in different settings. Okay. As I said in the first part of the talk, I will talk about some fundamental limitations of learning immersions. And this is joint work with my recently graduated PhD student Zixiang Liu and Eduardo Zontag from Northeastern University. Okay, so what is a linear immersion? This is the basic idea behind Koopman embeddings as well, if you are familiar with those. Here is how it works. You have a nonlinear system. You are trying to find a function psi such that you lift the state space of this nonlinear system X into some space Z. And you want the dynamics of this Z to follow some linear dynamics. And typically, you represent this psi with a neural network. And I am saying lifting because Z typically lives in a higher dimensional space, but it doesn't have to. And you try to learn this A matrix so that this linear system and nonlinear system solutions match in the sense that if I start my nonlinear system from an initial condition and flow it for a little bit, if I lift the state that I arrived at, it's the same as first lifting the initial state, flowing the linear system, and looking at where I arrive in the lifted system. And if I can do that, then I can do prediction for my nonlinear system using my linear system tool. And in case you have control, you can do control as well. So you have lots of tools on the linear system side. If you can find this equivalent representation, you can use many of those tools to analyze or design your nonlinear dynamics. But one fundamental question is, when does such psi exist? Does it always exist? And there are some results in Koopman theory that shows that if you are embedding in an infinite dimensional space, then such a psi exists. But in reality, we don't embed in infinite dimensional spaces. We just try to embed in a finite dimensional space. And we want to understand when such psi exists or not. The first thing I will point out is that this is not a well-posed question. So to give a good answer, we should ask better questions. And the answer to this question is, yeah, sure, it always exists. Take your psi to be some constant function and take your A matrix to be 0. Then you have a linear system that satisfies the property that I tell you. You lift your initial condition, you flow, you are still a constant. It's the same as flowing your nonlinear system and pushing it to a constant. What is wrong with this lifting? Why this is not super useful? It doesn't have an inverse, so it doesn't really give me any information about my nonlinear system. So ideally, maybe a better question to ask is that I want to find a psi that's one-to-one, so that I can do this prediction or control tests, or I can get some information about my underlying dynamics by doing this lifting. So we modified our question a little bit. Maybe this is a better question. Let's try to think about this question a little bit more. It might require a bit more refinement, but we will see what happens. So let's try to think through this through an example. Say I have a one-dimensional nonlinear system defined on the real line. This is my f of x, so it's positive over here, so my flow is in this direction. It's negative over here in this interval, my flow is in this direction, and so on. And this nonlinear system has 3 isolated equilibrium points. Now, the question is, can I find a one-to-one mapping to lift this to a linear system? One reaction could be, oh, linear systems never have isolated limit points. Maybe this is impossible. I will try to tweak that argument a little bit. Here is a 2-dimensional conceptual lifting, where my psi function is this one-dimensional manifold. My lifted system has infinitely many equilibria. It's a subspace, and this subspace intersects this lifting manifold in 3 different places. If I can achieve this, if I can find a rank-deficient A matrix, then there might be a possibility that I can represent this isolated equilibria with a lifted linear system. So just by saying, oh, linear systems don't have isolated equilibria doesn't really rule out existence that easily. And I will show you a numerical example following on this intuition. So here's a specific nonlinear system, one-dimensional with 3 equilibrium points. And I will give you a lifting function that lifts this to a linear system. So here is the lifting function. It's lifting into a 2-dimensional system. The function itself is a little complicated, but I will try to plot the function for you. What this function does is that it takes each of these intervals and maps them into this horizontal lines in my state space. Then it takes the 3 equilibrium points and maps them into these 3 points on the x-axis. And if you look at the A matrix here, this is a rank-deficient A matrix. So I have the subspace of equilibria, and that subspace corresponds to my x-axis. So this is exactly the picture that I drew earlier. There's a complicated, this is not even a single manifold now, there's a complicated lifting, but that lifting exactly intersects with my equilibria in 3 different points, and this exactly represents my dynamics, and it's one-to-one, I can go back. So the observation here is that it's possible to immerse nonlinear systems with multiple isolated equilibria into linear systems by using one-to-one mappings, but one property of this mapping is this is discontinuous. And what we will see is that this continuity has some power, that if we are restricting ourselves to continuous mappings, we lose some of this representation capability. So as I said, is discontinuity a good assumption? Practically speaking, no, because practically speaking, everyone learns this PSI using a neural network. Yes?
Sorry, interruption, but the previous figure, so how does the flow look like in space?
It just flows in this direction. Then the thing is like, since these are infinite flows, there's no finite time reachability to the equilibrium. So it just keeps flowing in each interval. So the time that you spend in each interval is infinite. So if you start here, you are just here. If you start elsewhere, you just keep flowing.
Does it reproduce this dynamics between the equilibria, which you see
Yes.
at the top?
So that weird thing here is just to make sure flow matches the exact dynamics. Here we are just adjusting the speed of the flow so that it exactly matches the nonlinear dynamics. Okay, as I said, the PSI that I showed you, it's discontinuous, but in practice, everyone learns this PSI using a nonlinear, using a neural network, and all the neural network activation functions that I know of, they are continuous. ReLU is continuous, tanh is continuous, sigmoid is continuous. So in practice, everyone is using a continuous PSI. With this, I will change my question a little bit, and I will ask, does there exist a one-to-one and continuous PSI so that when I try to learn this thing with a neural network, I will be able to learn? Before that, let me give you some definitions. You might know these from your nonlinear systems class or dynamics class. And these definitions will be relevant when I try to prove what I want to prove. So I will start with omega limit sets. So this is just a generalization of equilibrium points. We want to capture limit cycles and those type of objects as well. Given an initial state, an omega limit set is the set where as time goes by, your flow approaches to that set, roughly. I will also use pre-compactness of trajectories. Given an initial state, the trajectory starting from that initial state is pre-compact. If its closure is compact, you can think about it as boundedness. And there's a corresponding concept of backward pre-compact if your trajectory is not pre-compact, meaning if it's not bounded. But if you flip the time and if you run your system backward, that trajectory is pre-compact, that's still fine. We just want to avoid trajectories that come from infinity and go to infinity. Those trajectories will be problematic for what we want to do. And we have the definition of domain of attraction for an omega limit set. That's the set of all states, all initial conditions for which you are getting attracted to this omega limit set. With these definitions, let me try to ask now a more well-posed question that we will try to answer. We know that linear systems don't have more than one isolated omega limit sets. They either have a single equilibria or subspace of equilibria. Can nonlinear systems that have multiple isolated omega limit sets be immersed into linear systems using a psi that's continuous and one-to-one? So this is the question we will try to answer. Any questions on the setting? I think this question is precise enough so that we can develop an answer to this question. Okay. So here's a key definition that we use in the proof. We will call a system to have closed basins if the domain of attraction of all of its omega limit sets are closed sets. And you can show that every linear system has closed basins. And again, I am giving you a few examples here. I have a stable system here. The only omega limit set is the origin. The domain of attraction of the origin is R2, and R2 is closed. I have an unstable equilibrium point, repulsive equilibrium point here. The only omega limit set of this system is this equilibrium point. The domain of attraction of this equilibrium point is itself. It's a closed set. I have another system that has a stable manifold and an unstable manifold. Again, the only omega limit set is the equilibrium. The domain of attraction of this omega limit set is the x-axis, and it's a closed set. And you can show that all linear systems, they have closed basins. Even if they have single equilibria or subspace of equilibria, the domain of attractions of these objects are all closed sets. Now, given this, here is the main theorem. If the state space that you define your nonlinear system is connected and forward invariant, and if your system can be immersed into a system with closed basins using a one-to-one mapping psi, one-to-one and continuous mapping psi, and if the trajectories of the systems are pre-compact in your domain or backward pre-compact, and if W is the set of all omega limit sets in X, and if this W set is countable, then W has exactly one element. In other words, if this psi is continuous and one-to-one, and if the trajectories of this system is bounded either forward in time or backward in time, and if F has countable but more than one omega limit sets, then F cannot be immersed into a linear system. Arguably, the thing that makes nonlinear systems interesting is having multiple equilibria. And this is saying if your nonlinear dynamics is interesting enough, you cannot immerse them into a linear system if you are using a continuous and one-to-one lifting function. So these conditions that we have are sufficient, but they are almost necessary as well. And I will tell you why they are necessary in certain sense. If I didn't restrict psi to be continuous, I already showed you an example. With this continuous psi, I can find these one-to-one mappings. So that's necessary for non-existence. I need to search for continuous psi. When trajectories are neither pre-compact nor backward pre-compact, meaning there exists some trajectories coming from infinity and going to infinity, then there are examples in the literature that shows that there exist this immersions that are continuous and one-to-one. So that pre-compactness assumption is needed as well. And if F has uncountably many omega limit sets, I already have linear systems that have that property. So there's trivial liftings that are identity that will give me linear systems. So in a sense, all these conditions are necessary for this negative result. Let's also look at some implications of this. So what does this tell us in terms of like learning these objects? If you are using a neural network with continuous activation function, one thing I didn't show in the theorem, but we prove in the paper as well, this function will collapse all the omega limit sets on top of each other. So the function doesn't have the ability to differentiate omega limit sets. Therefore, it won't be one-to-one. So it will collapse these omega limit sets on top of each other. There's a trick that people use to enforce one-to-oneness because you want to get something that you can inverse. You can go back to your nonlinear dynamics. And the trick is as follows. You take your psi, and instead of trying to learn psi, you say my psi has a specific form. It has my x in its first couple of coordinates, and it has some phi, and I will fit a neural network to this phi. So this structure is nice because it gives you one-to-oneness directly, and it has a very simple inverse. Inverse is just projection, so you don't need to worry about how to invert that as well. And sometimes systems that admit this type of liftings are called superlinearizable, because this is a little more than linearizability. But what our result is showing is that if you try to learn something with this structure, then this phi that you are trying to learn, it has to be discontinuous. It cannot be continuous. So if you add more and more data, you are forcing your neural network to be discontinuous. Of course, because of the activations, it cannot be discontinuous, but it will have very high Lipschitz constants. And we know having high Lipschitz constants, it degrades your robustness. So it won't be a reliable object that you are learning. Yes.
So the first bullet point basically means that you cannot even have a good approximation with a linear system, right? Because if everything is being collapsed into one. So we know that there does not exist a linear system that matches. But another follow-up question would be, do we have a linear system that is
close enough? This doesn't say anything about approximation, but I will have something that shows that's more learning focused. If you just blindly learn, you are really enforcing this collapse. So we have there's going to be a learning result in a bit. Blindly learning with a continuous parameterization of the lifting enforces collapse. Other questions? Okay, so far, so before that, let me show a few other examples. This is a nonlinear system with two equilibria. If I take my domain to not include one of the equilibria, but everything to the left, I can define this lifting that gives me linear dynamics. Everything is fine. As long as I include the second equilibrium point, this lifting is no more defined there, so it doesn't exist. Here is another example. This example is interesting in the sense that this is a nonlinear system that has an isolated limit cycle. And linear systems don't have isolated limit cycles. They will have a continuum of limit cycles. You can think maybe this is just a simple topological trick. I am not able to change topology. But I will show that as long as I don't take the equilibrium point in the origin, I can embed this to a linear system because it will only have one omega limit set. And at the moment I include the origin, there does not exist a linear embedding. And this is the linear embedding to a three-dimensional space of this nonlinear dynamics everywhere except the origin. This is well-defined and matches the dynamics perfectly. But at the point that I include 0, this embedding becomes ill-defined at 0. So this is not a valid embedding in the entire space where I have two omega limit sets in this case. Okay, so everything that I said so far, although I said it has some implications in learning, but I didn't say anything about learning. I was talking about this continuous state spaces and fitting functions everywhere in the space. Now I will try to define the result a little bit and make it more related to learning. So to learn, we need some data. So here is how I will define my data. I have a state space. I will sample some points and points in my state space and initial conditions in my state space. Let's call them XL. I will pick a sampling time, tau, and I will flow my dynamics from XL for tau units of time, and that will give me XL plus 1 or XL plus. And I will try to solve this optimization problem, where I am searching for a continuous psi, and I am searching for A such that this flow matches the nonlinear flow as closely as possible. Let me go on more step. We know this optimization problem always have solutions because as I showed you earlier, I can pick this psi to be a constant function. I can pick it to be 0. Then I can pick A to be 0, and that's a trivial solution. And the trivial solution achieves 0 objective. So any optimal solution of this optimization problem achieves 0 objective. And now I will define the set of all optimal solutions. And this is the projection of the set of all optimal solutions on this lifting functions. And I will call those functions interpolating functions. And I will parameterize that set with n. N is the number of samples that I will keep increasing if needed. And one other note here, you might say, oh, this is a trivial solution. No one will solve it. They will put some extra constraints. It's fine to put extra regularization or constraints there. What I will show you is that this set cannot include certain functions. And if you add more constraints and make the set smaller, it will still not include those functions. Okay, so in this learning setting, we have a similar result. If the number of points that I have is dense in my state space X, and if this psi is a continuous function that can differentiate omega limit sets, it's a function that doesn't collapse omega limit sets, then there exists a small enough sampling time such that if my sampling time is less than that threshold, there exists a finite n such that any function that differentiates omega limit sets cannot be in the set of optima. So this is saying that if you start learning and adding more points, and if you are fitting your data perfectly, then you have to collapse omega limit sets. Okay. Okay, so this concludes the first part of the talk. So what we showed is that under mild conditions, for nonlinear systems with multiple isolated omega limit sets, there are no linear immersions that are continuous and one-to-one, even if A is low rank. A being low rank saves you if you use discontinuous liftings, but it doesn't save you in general. And this has some implications in terms of learning. Maybe if you want to learn this complicated dynamics, you need discontinuous psi. So some hybrid structure is required. So you either lift with a discontinuous thing, or instead of lifting with a linear structure, you use a continuous lifting, but you lift in a piecewise defined structure. These are both feasible strategies. But if you insist on, oh, I am going to lift in a linear system with a continuous lifting, our result shows that it doesn't work. And we have, motivated by this, we have some follow-on work where instead of trying to learn this global lifting, we are trying to learn local liftings. And we are also looking into some approximate liftings, and we can do some constrained reachability tricks by learning those local liftings. And in a sense, this is generalizing your typical local linearization. Instead of just linearizing in the current space, you can lift and linearize, and you can get much larger domains where these linearizations are valid. Another question we are looking at is that if you have multiple approximate Koopman type liftings, how do you compare them? Is there a notion of one is better than the other? And we are trying to develop some order relations between these liftings so that we can incrementally improve if we are not happy with the current representation. And here is some simulation using this idea of hybrid liftings. We have an unknown dynamics. It happens to be a pendulum. And if you just learn local linearizations, you can recover some reachable set, which is small. And if you do this lifted linearizations, you almost recover the entire reachable set. And the number of local linearizations you need to learn is 2 orders of magnitude less. And you are achieving a much larger reachable set. Okay, so this is a good place to stop if there are questions.
There's a big question. So the examples you were
Mhm.
looking at, you actually already knew the dynamics, right? So
Mhm.
you said, okay, there's a mid-cycle, there's
Mhm.
isolated equilibrium, but
Mhm.
then also you know what to exclude, right? In
Mhm.
some sense, if you wanted
Mhm.
to achieve your goal.
Mhm.
But if the whole point is learning,
Mhm.
then I typically don't know that state-space picture, right? So then how do you in advance figure out how to do these things?
So one thing you can possibly do is, this is all about like region of attraction, right? You should be learning in the same region of attraction. So you can simulate your dynamics and include points that are getting clustered in similar places. And there are results, there are very recent results actually. There's this Hartman-Groupman theorem that's, so Eduardo has a very recent result that generalizes that to beyond hyperbolic. So in any region of attraction of an equilibrium that's stable, there is a linear immersion. So if you can localize, of course, if you are very unlucky and you have like two equilibrium that are very close to each other, and if you cannot differentiate with your data, maybe you are in trouble. But otherwise, you can try to cluster your data based on where you are converging and learn locally based on that.
Also imposing a finite dimension for Z.
Yes, yes.
Is that why this is different from Koopman?
Yes, so the theory says infinite dimensions, and typically it's uncountably infinite. But in practice, this is what you need to do. And you should be careful if you are doing this. So that's kind of the message, I guess.
Could you give an idea of how you can choose among the multiple Koopman liftings, essentially the ongoing work that you have at the bottom?
So it's a little complicated, but essentially what we are looking at is, we are looking at compact domains, and we are trying to define behavior inclusion between these liftings, and we are using ideas from like simulation relations, bisimulation relations that defines the pre-order in the space of Koopman liftings. Other questions? Okay, now I will switch to the second part. So this was an impossibility result. Now I will show you a hardness result. And I will show you when learning to stabilize linear systems can be hard. So since I am going to talk about hardness, let me tell you how to measure hardness. So computer science people are very good at coming up with measures of hardness. One measure of hardness is computational complexity. And computational complexity asks how the computational cost of an algorithm depends on the input size. And you will see this big O notation and different computational complexity classes like P, MP, X, and so on. Another notion of hardness is sample complexity, and that's relevant to learning. And we will work with sample complexity in the remaining part of the talk. And sample complexity asks how a performance metric of a learning algorithm depends on the number of samples. And there are different performance metrics you can use. For example, if you are trying to learn dynamics, if you are trying to do SysID, maybe your performance metric is the approximation error. If you are trying to learn a controller, an optimal controller, maybe the cumulative cost or regret gives you a performance metric. And in this work, we will use probability of the stability of the and closed loop as our performance metric. So these are complexity measures for a given algorithm. These can be generalized to the complexity of the problem. And the complexity of the problem is complexity of the best possible algorithm. So you might have an exponential time algorithm for solving a problem and a polynomial time algorithm for solving the same problem. Then the problem itself is polynomial time. Your algorithm can still be more complex. And we will look at sample complexity of learning to stabilize linear systems in this talk. Okay, so here is the setup. I am given a discrete time linear system. It's time invariant. And I am given a system from some class Cn, and I will define this class later. So the system is subject to some Gaussian noise. I am given a time budget n, so I will interact with this system for up until time n, and I will have a budget on the input that I will use. I don't want to inject very large inputs and increase my signal to noise ratio too much and cheat that way. So I will put a budget on the inputs as well. And I will consider a learning algorithm pi that interacts with the system for n units of time. And at the end of this n units of time, the algorithm will output a static state feedback controller k hat. And I want to know what is the probability of this k hat stabilizing my unknown system as a function of n. And you can use your favorite algorithm. So this is kind of the setting. There's an unknown system. There's this algorithm that interacts with the system. The algorithm is pi. This algorithm can excite the system for n steps and do something like direct data-driven control or RL. It can excite the system for n steps and do system ID based on that and do certainty equivalent control from the learned dynamics. Or you can try to be more fancy, use some online active learning method where you interact a little bit, collect data, and pick your interaction strategy based on the collected data. And from with the thing that I will show, it doesn't matter which of these algorithms you use. There's a fundamental hardness in learning, and that's what we are going to try to establish. Okay. Here is the problem statement. As I said, this algorithm outputs a k hat. This k hat is a function of what I have seen, the data that I have seen from the algorithm. And there's going to be some probability of this k hat stabilizing my system. It's probabilistic because k hat is a random variable. It's a function of the random data coming from my system. The learning algorithm pi, to evaluate it, we will look into the worst possible probability here, because if A and B are nice enough, maybe this probability is high. We will look at over this class, the nature picks the worst possible system S. And we want this algorithm to work still reasonably well for the worst system that nature can pick in my class. And to measure the sample complexity, this is what we want. We want to figure out the minimum data or time budget n, such that I can make this quantity arbitrarily large. I am given some delta, and I want to make this quantity arbitrarily large. Now, the question is, given a class of linear systems, if C is just linear systems AB, how does this sample complexity for learning to stabilize a static state feedback controller depends on the system dimension n? Is it a polynomial dependence or is it an exponential dependence? If it's exponential, maybe I am in trouble because that means I will need lots and lots of data to be able to stabilize with high probability. Okay, any questions on the setting? So here is how we will establish hardness. We will find a class Cn within the class of linear systems that's parameterized with n. So I want to be parametrically increase the size of my system so that I can show you the dependence on n, such that this, to achieve stability with high probability, I will need number of samples that grow exponentially with the dimension n. And the answer to this is kind of very intuitive. When hardness occurs is kind of very intuitive. A class is hard to learn or to stabilize if it contains a pair of systems that are both hard to distinguish and they are not co-stabilizable. If these two conditions hold, then this is hard to co-stabilize. And again, these two conditions are almost necessary and sufficient in the following sense. If these systems are not hard to distinguish, then I can do system ID and I can learn them quickly. And if I can do system ID, I can learn the system, then I can design my controller with the learned system. If they are co-stabilizable, then I don't need to learn to differentiate these systems. I can have a coarse learning, but I know even if I learn in a coarse way, there exists a controller that stabilizes both. So I don't need to do the learning part that well, sysid part that well. I just design a robust controller that co-stabilizes, and I am done. But if both of them fails, then you are in trouble. If both of them is hard, then you are in trouble. And for distinguishability, we will use this notion. Two systems are hard to distinguish. If I am deriving them with the same type of policy, they generate some trajectories, and there is a distribution over the space of trajectories. And if this distribution of trajectories they generate are similar, it's hard to distinguish them. And co-stabilizability is a very fundamental thing from robust control. That's the existence, or in this case, not co-stabilizability, is non-existence of a single controller that stabilizes the two systems simultaneously. In our case, we will look for static state feedback controllers, and not co-stabilizable essentially means this thing. Okay, here is kind of the construction of these two, the pair of systems. It's essentially a first order system with a bunch of delays. And that delay is going to be my parameterization. And these two systems only differ by the first entry in this B matrix. And one thing you can show is that to make these systems co-stabilizable, you should make this difference exponentially small as n increases. And you can do this by undergrad control techniques. You just use Ackermann's formula to figure out how you place the pole with a controller. Then you do jury stability tests. And you can figure out you really need this exponential closeness to be able to co-stabilize. But if this is exponentially close, then it's so similar to each other that it's undistinguishable. So if you can co-stabilize, you cannot distinguish. If you can distinguish, you cannot co-stabilize. So here is just numerical sanity check as well. You can solve an LMI to figure out how this M changes with dimension. Okay, here is the main theorem. It's a little complicated, but if your class of systems contain these type of one-dimensional systems with delays, then to learn to stabilize with high probability, you need exponentially many samples in the dimension of the state space. And this is just your signal to noise ratio. Of course, if you have more input power, you will learn faster, but you cannot get around this exponential complexity up there. So this is just illustration. We just picked one learning stabilization algorithm. We applied it, and we also observed this exponential need for exponential number of samples in practice. Okay, here are some takeaways from this part. Learning to stabilize a linear system is hard if we have systems that are hard to distinguish and hard to co-stabilize. And this generalizes some of the earlier work in the literature, and it really brings more control theoretic understanding of what makes things hard. I lied to you a little bit in the sense that I only showed you it's hard to stabilize if I am searching for linear state feedback, static state feedback gains. But one thing we know from robust control is that although linear static state feedback gain is sufficient for stabilization, it's not rich enough for co-stabilization, in the sense that there are systems that are not co-stabilizable with a single linear static state feedback controller, but that are co-stabilizable with controllers with memory. So maybe this hardness is because we are searching in the wrong space of controllers. And that's something we are looking at right now. So again, this is maybe a negative result, but I think it's a good outcome that we realized people were, including us, we were looking at the wrong class of controllers to blame the problem on the learning problem, but maybe the problem is the type of controller that we are picking and trying to learn. Okay, so this kind of concludes the second part. As I said, learning is very exciting and it can affect your control loop in many different parts. But it's always important to be aware of fundamental limits. And there had been lots of foundational work in Michigan thinking about fundamental limits. And I think once learning is in the room, we can still go back to fundamental limits and think about them. And I think if thinking about these fundamental limits will help us learn better controllers or better systems. I think with that, I will stop and I can take questions.
Does your results on the hardness of stability, does it have any implication on the partially observed systems?
Yes, trivially, in the sense that if you observe the state, it's hard. It cannot be easy if you are partially observing the state.
Can we say anything beyond that?
Is it harder than exponential? We didn't look at that. I don't know what is the measure to use there, maybe. I can easily say it's exponential if it's partially observed. But if it's yeah, I don't know how the exponent will change.
Big question about this last topic when you mentioned that it's exponentially harder to learn, but what about nonlinear systems? So if I think about the simplest possible case, I still have one equilibrium, right? But I have a system either, let's say, a polynomial nonlinearity, so there's kind of weaker convergence, right? Versus I have some kind of square root-ish nonlinearity, which is stronger convergence, but typically non-Lipschitz. So what is kind of the feeling about it? Which one of these is gonna be potentially better than the one you're looking at?
So for the Koopman part or?
For this part, the learning part.
For the learning control part, this is only talking about, I didn't talk about system being nonlinear. System being nonlinear is a different beast. I am still talking about system being linear, but the control we should look at should be more complex than static state feedback. I don't have that much intuition on what happens with nonlinear systems. There are some results though with as you mentioned, stability makes things easier to learn. And I think some of these results as well, they depend on rate of convergence. Yeah. I would imagine rate of convergence will affect the learning. But this is more about the class of controllers you should be looking at is different than static state feedback if you're in the learning setting.
Okay.
You can go.
About the class of systems, what happens if you do a change of variables or a remapping? Is this independent of whether you do a change of variables?
So for the second part, the thing is, since this is state feedback, change of variables will change what I am observing as a state. So in that sense, it matters a little bit because you can.
It's the same, right? Ultimately, if it's a change of variables, it should be the same system under a different controller. But the hard to distinguish will change. metric will change.
So there are a few subtleties there in the sense that like you do a change of variables to your state, then to get the same type of output, you need to do a change of variables to your noise map as well, because I am using the noise statistics there. Then if you are making the noise such that it's exciting a direction a lot, it might change things a little bit, because like change of variables will change my noise statistics too.
On like the necessity of this. So if you look at like the space of systems that need at least exponential number of samples to learn, in this case, to be able to stabilize with worst case performance. And then sort of the results where the intuition, which is pretty good intuition, that if there's ghost stability and you're not able to learn, then these systems are hard. Is there a sense sort of the density of this parametric systems that you have in the sort of all systems that need exponential time steps?
That like even defining all like that looks like a piece to define the set of systems is it's a very weird infinite dimensional space. I don't even, if you go beyond parametric, things are strange. And the other thing is like we are specifically looking at like you need a finite notion of a state that you can parameterize and you can increase the state. So I think there is no direct mapping of this to non-parametric settings, because I really need a Markovian state. I need to define a Markovian state to start with. But it might be interesting to bring in some like non-parametric uncertainty somewhere, but this doesn't extend that easily. But you can do the following. If you have a parametric set, then within that set, you should look at distinguishability and cost stabilizability. If that's a set that you can analyze distinguishability and cost stabilizability, similar types of proved structure goes through.
So distinguishability and cost stability, is it necessary in this case?
Yeah,
The hardness result is
yeah.
necessary.
For hardness, if one of them is easy, the problem is easy.
Here's me again, and snowboarding lessons.
Don't take snowboarding lessons from me.
He's a visiting student. Sorry. Just arrived this week. Rather than trying to find and decide first. Can you do something there that starting off with linear. Yes, they can. So I am going to say. So yeah, this is. I mean, to spread over offices. But it's not public like that.
I think the most thing that we're not trying to learn the other thing. Learning is always possible. There is always a perfect interpolating thing. And interpolating thing will start collapsing stuff and it be non-perfect.
Definitely the experimental spaces are.
Of course.
Have to be pretty put together.
Would be possible because we know.
Oh, yeah, but that's just like more silent, right? It's like
Naming area.
Also, okay, it looks good. Other one.
Is this the wrong approach to learning like a interpretation?
I think
I figure we need to learn the sets over which these.
I think that was like what the board was asking. So It's like your data around where different things are converging. So you can use like this. But if you're in that basin of attraction, there you can do.
We're in the same vein.
So each other might not be able to distinguish that.
My worry is that, you know, we.
Yeah.
You might run into trouble.
And the other case was when you have the isolated limit site. Other basin has no domain where you learn.
Yeah. You will probably learn the other thing and but again, you said the origin, so neural network that can learn it will have very high Lipschitz constant because we are approaching the like I think the all the data you collect from around the origin, larger Lipschitz constant you will get.
Yeah, and you also need to be able to say, I need to exclude some region around equilibrium point if you want to use the sense.
But in that case, as long as you don't, the origin is not
Particular one.
your data set, we are fine, you will be able to learn.
But in the other case where you have like a one case, like the split happens at x equals 1, and you have to make sure you don't sample any points on the other side. of the x equals
Yes.
1, right?
If you- Or like you can sample and you should check that, oh, these are going in the same direction, but these are not converging to that direction. I shouldn't use these two data sets to learn one thing together.
Keep talking.
Yeah, I did.
I see. Hoping that you went at least put some. And I'm waiting at some point, like maybe like the lesson people like the hyper learning organizations. Next point, like we have to start by slowing the next year. Okay, we're still learning the system that is.
That's interesting.
Really?
Fine. If I remove points, then I get a disconnected space. So the proof doesn't go to R2, if you remove,
You never know, but you know, yeah. No. I was thinking.
like if you R2, you might have this.
Yeah. When everybody from out.
Like trajectories that come from infinity and go to infinity. If you have something like that, that also R1 doesn't include that.
But right now, I think it's the lack of amount of. For the case for we're able to move it.
Yeah.
Okay. Otherwise, this might be if I have a discrete mapping instead of continuous time mapping. Does the different systems results come in like exponents?
I think so, we didn't prove that, I get this question all the time, I don't see anything in the. That don't work.
For me, it was a visualization thing that for the environment we are gonna set up.
Yeah, and then we'll have also Jose.